I am R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this video, we are going to see the topic Smith chart and applications for the course Transmission Lines and Antennas. So, how to find the parameters of a transmission line? So, we can use numerical calculations, difficult to use formulas and difficult to do calculations in a transmission line because they involve complex terms and takes a lot of time to compute. So to overcome this, we need a solution. The solution must be easy to use without tedious calculations, and also it must be time consuming. So here the Cartesian signal circle diagram is one solution for this to overcome this problem. So here the range of impedance and admittance values are limited, and the interpolation of constant S circles and constant beta S circle on this chart is difficult and inaccurate. So in order to overcome these problems of Cartesian circle diagram, we are going for a method called Smith chart, and this is also called as transmission line calculator. So this was designed by P.H. Smith in the year of 1939. The main aim of this chart is to overcome the drawbacks in the Cartesian circle diagram, and it is a graphical tool for use with transmission line circuits and also microwave circuit elements. So here only lossless transmission lines will be considered, and this chart is obtained from the reflection coefficient equation K mod angle of phi minus 2 beta s is equal to u plus jv. And there are two types of circles in this diagram. One is called constant R circles, which is shown in the diagram, or this is also called as constant resistance circles. And the next family of circle is constant reactance circles or constant X circles. So the combination of constant S circle, R circle and X circles is called a Smith chart. That is, Smith chart is nothing but the superposition of two circles, two family of circles. One is constant R circles and another one is constant S circles. So this is the picture of Smith chart. We can observe the two family of circles, and this Smith chart is in the middle we have a line. So this line is called real impedance axis, and the center of the Smith chart is always 1, and imaginary impedance circles are shown in the diagram. And in the picture we have a distance along the transmission line. So here the distance is in terms of lambda. So all the length in the transmission lines are obtained in terms of wavelength, and angle of degrees reflection coefficient is given in the picture, and reactance value. So upper reactant in the real axis, so above the real axis, that is upper half of the circles gives the reactance value, inductive reactance, and it is denoted by plus JXL, and in the lower half of the circle is the reactances are capacitive reactance, and it is given by minus JXC. So center of the Smith chart is always 1 plus J0, that is no imaginary part. One is the real value is 1, and this is the Smith chart. So below the Smith chart we have a scale for finding the magnitude of reflection coefficient. And the properties of Smith chart. Smith chart can be used as an impedance chart or also the admittance chart. In Smith chart, all the impedances are normalized impedance, that is dividing the impedance by its R0 value, the characteristic resistance. And we know the center of the chart is 1, 0. Real axis, that is the horizontal axis in the middle of the chart, represents the resistance or the real part of the impedance value, and imaginary circles represents the reactance. Upper half imaginary circles inductive reactance, lower half imaginary circles are capacitive reactance. In Smith chart there are 3 concentric external circles Innermost circle on the inside of the circle are graduations of inductive and capacitive reactance, and after that we have a second circle which will be represented by the reflection coefficient value in degrees. And next is third circle, graduations represents distances along the transmission lines in terms of wavelengths, and the total length of the entire chart, Smith chart, is 0.5 lambda, that is half of the wavelength. And clockwise motion in the chart represents the length value towards generators, and anti-clockwise direction is represented the wavelength value in terms of load, towards load. And Vmax is represented at the right side of the chart, and which is the infinite impedance or open circuit condition, and V minimum is at the left side of the chart, which is the zero impedance or short circuit condition. And the applications, they are used to find the magnitude and angle of reflection coefficients, and to find out voltage standing wave ratio we can use Smith chart. And unknown load impedance and admittances are obtained, unknown input impedance and admittances are obtained, maximum voltage, minimum voltage levels are obtained from the Smith chart, and this is also useful in stub matching. So the applications of Smith chart. So consider a 20 meter long transmission line with a characteristic impedance 50 ohms operating at 2 megahertz. If the line is terminated by an impedance 60 plus j40 ohms, calculate the reflection coefficient K, standing wave ratio S, input impedance of the transmission line. The velocity of the line is given. So here length is given 20 meters, Z0 is given, F is given as 2 megahertz, and velocity value is given, ZL is given. We have to find out K, S and ZS. So step 1 is finding normalized load impedance, because in the Smith chart all the impedances are normalized impedance. So first step is finding ZL by Z0. So 60 plus J40 ohms, ZL value is divided by the characteristic impedance value 50 ohms. So we get 1.2 plus J0.8. So 1.2 is the real value, 0.8 is the imaginary value of the normalized impedance. So we have to locate the point P on the Smith chart, where the 1.2, the real value from the real axis, that is in the middle of the Smith chart, and in the imaginary circle it is inductive reactance. So we have to find from the upper half. So both will meet at point P, which is marked as load impedance as shown in the diagram. And the second step is finding SWR. In order to find SWR, we have to mark the center of the chart as O, and SWR obtained by drawing S circle with the center of the chart with radius equal to the distance between O and P. What happens is the circle cuts the real axis at the right side, gives the value of standing wave ratio. According to our problem, it is 2.1 approximately. So the S circle at the right side, we can get the SWR value 2.1. And third step, angle of reflection coefficient is obtained by extending OP to the outer rim of the chart, the point at which the line cuts the outer rim, that is second concentric circle where the reflection coefficient angles are given, gives the K value in degrees. So here angle of K is 54 degrees approximately. And next is to get the magnitude of K. For getting magnitude of K, the distance between O and P is taken by using a compass, and the K scale is provided at the bottom of the chart. From the center, draw an arc from the center scale at the right side. This gives the magnitude of K, it is 0.34. So by combining this magnitude and angle value, K is written as 0.34 angle 54 degrees. So in the scale, magnitude of K is obtained by 0.34. So step 5, for getting input impedance, the length value is obtained in terms of lambda, by dividing L by lambda value, it is 0.22 lambda, and we have to get the input impedance. So from the load impedance we have to go towards generator, that is clockwise direction. We get by the distance 0.22 lambda, we get the input impedance. It is 35 minus j 26 ohms. So in this way, Smith chart is used to obtain all the unknown values without tedious calculations. Within a very easy steps we can get the values. Thank you. And for impedance to admittance conversion, we can get diametrically opposite point of impedance in the chart gives the admittance value. So, assessment. The Smith chart is a graphical technique used in the scenario of transmission line. Say true or false, that is true. The Smith chart consists of, we know, two family of circles, constant R circle and constant X circle. So the value is, the answer is A. The circle in the Smith chart passes through which point is, we know it is 1, 0, the answer is D. Moving towards the clockwise direction in a Smith chart is towards generator. Thank you.